Hello everyone, welcome back to Physics 425. What I want to start with today is a description of a possible experimental setup that can be used to reach temperatures of about 1 Kelvin using a bath of liquid helium. Just to recap, last time we were thinking about how we could manipulate the boiling temperature of a liquid by changing the vapor pressure above that boiling liquid. And what we found was that the relationship between the pressure and temperature was given by this expression. B was some constant, but pressure had an exponential dependence on minus 1 over the temperature. Okay, and so that's something that we will keep in mind. So here's the apparatus. We're going to start with a dewar, and this dewar has a double wall. It's similar to what you would keep your coffee in, a thermos that you might keep your coffee in. So if we were to zoom in onto a part of this dewar, what we would see is a solid glass wall, and then an empty space that's been evacuated, and then another solid wall. Okay, and so in here is vacuum. Okay, so these dewars can be made of metal or glass. And then what we're going to do is we're going to put another similar dewar that fits inside of the first one. Okay, and it's going to extend a little bit out above. And again, it's another double-walled dewar with a vacuum space in between the two walls. Within the first outer dewar, we're going to fill it with liquid nitrogen. Okay, and so this is filled with liquid nitrogen. This dewar is just open to the room, and so nitrogen is constantly boiling and nitrogen vapor is coming off. And so inside here, it's about 77 Kelvin, and this is liquid nitrogen. Okay. Inside the other dewar, we're going to fill it with liquid helium. And again, helium will be evaporating off of the surface of the liquid, helium gas. And what we're going to do is, if that was just at an atmosphere of pressure, then the liquid helium would be at a temperature of 4.2 Kelvin. But what we're actually going to do is we're going to seal the top of this dewar, maybe using O-rings or something like that. The top of the dewar is at 300 Kelvin. It's just at room temperature. But then on this top seal, this flange, we're going to connect a pipe that goes to a pump. And I'm going to use a symbolic symbol for a pump. So here's a pump. In practice, this will be some long tube that goes to a nearby pump. And if you want to get to as low as possible temperature, you want your tube to be large diameter and you want your pump to be large and nearby. Okay, and so we turn on the pump and we reduce the pressure above the boiling liquid helium. And if we can do that, we can get to maybe 1.1 Kelvin or something like that in the helium bath. Also attached to the flange, which I haven't drawn, is going to be your experimental apparatus, and there may be some tubes running from the flange that go into the liquid, and your experiment's at the end of those tubes submerged in the liquid. Inside of those tubes, you'll run whatever electrical wiring you need to operate your experiment. Okay, I'm going to come back to this picture in just a little bit, but there's, a rough schematic of an experimental setup. What I'd like to do is to try to calculate something called the cooling power of the pumped liquid helium-4 bath. What the cooling power is the heat removed per unit time. The reason this is relevant is because whatever your apparatus is, whatever experiment you're doing, if you try to cool it to low temperature, inevitably there's going to be some heat load on your apparatus. There's going to be heat conducted down different pipes and wires in your system, and we'll actually identify some other sources of heat, but there's going to be some heat absorbed by your experiment. And at the same time, your low temperature apparatus is designed to remove heat at a certain rate. In equilibrium, the amount of heat that's being absorbed by your apparatus and the amount of heat that's being removed by your low temperature system are going to be equal, and that's going to determine what your base temperature is. So it's important to know this cooling power, and it's going to be the heat removed per unit time. For our liquid helium bath, it's going to be the rate that particles evaporate from the liquid, so the rate that particles are converted from liquid to vapor. During that phase change, an amount of heat, the latent heat, equal to the latent heat is going to be removed from the bath. So if delta Q is this latent heat, then for each particle that is converted from liquid to vapor, then we remove an amount of heat equal to the latent heat per particle. So this is the heat of vaporization per particle. Remember, the latent heat was the heat needed to completely vaporize the entire amount of liquid. Okay, so recall that, the change in enthalpy was equal to the change in heat for a constant pressure process. So here we're imagining that we've been running our pump for a while, so that we've reached some equilibrium pressure above the liquid, and in this condition, the latent heat is equal to the change in enthalpy, and so delta Q is equal to the change in enthalpy, which we'll call the latent heat. And so that means our cooling power becomes the rate of evaporation times the latent heat per particle. Okay. What I'm going to do is I'm going to divide n, the number of particles, divided by Avogadro's number. And so this we'll define as little n, which is the number of moles. Okay, if we divide by n, then we have to multiply, if we divide by Na, we have to multiply by Na, and I'll do that by dividing the denominator of the next factor by NA. And so then what we get is that our cooling power is N dot times the latent heat per mole, or the molar latent heat. Okay, the next thing we need to make note of is that usually pumps remove gas at a constant volume rate. What that means is, if you were going to go purchase a pump and you're researching your different options, one of the key specs that you'll see is called the pumping speed, and that tells you how much volume is removed, say, per minute or some per unit time. So pumping speeds of a typical mechanical pump might be something like 10 cubic feet per minute. Which converted into liters is about 300 liters per minute. Of course, this specification will vary depending on the type of pump and the size of the pump. But in any case, the pumping speed is usually approximately constant over a wide range of pressures. So that means if you turn on your pump and initially the pressure is in atmosphere, and then you run it for a while and you get the pressure down to 1/100th of an atmosphere or something like that, the rate that it's removing volume, the V dot, is not changing much. Okay, so for a low pressure gas, we can make use of the ideal gas law. So now we imagine we've turned our pump on, the vapor pressure is low, and the ideal gas law is a good approximation. So it's N kBT over P is the volume. In terms of molar quantities, or the number of moles N, we could write it as little n RT over P, where R is the gas constant. So if we have reached equilibrium, then T and P are approximately constant. So that means we've been running our pump and we reached a constant pressure above the liquid. So the rate that we're removing vapor particles with the pump is completely offset by the rate that particles are being added to the vapor by evaporation from the liquid. And so if we're evaporating liquid at a constant rate, then and we have a constant pressure above the liquid, then the temperature, the boiling temperature, is going to be constant. And in that case, V dot is just equal to N dot RT over P. So the rate that we're removing moles of particles from the vapor is equal to the rate that the number of moles the moles per unit time that particles are leaving the liquid by evaporation. What that means is then that N dot is proportional to pressure, so that our cooling power, if we go back and look, here's Q dot, and here's our cooling power expression, N dot, times the molar latent heat. I'm just going to do this as a proportional. Is proportional to N dot, but N dot is proportional to P times the molar latent heat. But if we look up our expression for P from the beginning, P had this dependence on temperature, e to the minus 1 over temperature. And so this is proportional to e to the minus 1 over temperature. So if we were to plot this function, so here we go, cooling power Q dot as a function of temperature, this exponential to minus 1 over T. So let's imagine at really low temperatures, then 1 over T is large, and so e to the minus a large number is small. So out here, the cooling power is really small at low temperature. At high temperature, 1 over a large number is small. E to the small number is quite a bit larger. And so this looks something like that. And so the important point is that the cooling power of the pumped liquid helium-4 bath decreases rapidly as you go to lower and lower temperatures. Okay, once you're at low temperature, you eventually reach a point where the power that can be extracted from the bath by evaporative cooling is insufficient to offset the heat load. And at that point, an equilibrium temperature is reached. And so if you wanted to get to any lower temperature, you'd have to do one of two things. You could get a bigger pump so that you can increase your pumping speed and lower your pressure and get to slightly lower temperatures, or you reduce the heat load that's being dumped into your bath. And so let's go back to our original picture here, and let's see if we can identify some sources of heat that are being absorbed by our bath. Okay, one source of heat is we're at room temperature at the top of this inner dewar, and so we can conduct heat down the walls of our glass dewar. And so here is some conduction. You may also have some residual gas inside of the walls of your between the walls of your supposedly evacuated dewar. And so residual gas can also conduct heat from the 77 Kelvin surface on the outside to the low temperature surface on the inside. And so what we could have is conduction by residual gas. One interesting point is that if this residual gas was air, then as soon as you started cooling down your apparatus, all of that air is going to freeze out. So the oxygen will stick to the walls because oxygen freezes at a temperature above 77 Kelvin. Once you put the liquid helium in there, the nitrogen will freeze out, and the only thing that's going to really cause you a problem is helium gas. And so typically what you would do is before an experiment, you would open the Dewar vacuum space, the inner Dewar vacuum space, to air, and then pump it out, then let air back in, pump it out, let air back in, pump it out, let air back in, pump it out, so that you're sure that whatever gas is left in there is air, which will freeze out once you start your cooling process. The reason why it might fill up with helium is because if after you've done an experiment, all your liquid helium is evaporated, but you have a bunch of helium gas in your inner Dewar, if your Dewar is a glass wall Dewar, glass actually becomes permeable to the helium gas at room temperature. And so if you're leaving it sit there for days at room temperature with helium gas trapped in the inner Dewar, it will diffuse through the walls and enter that vacuum space. And so it's important to flush that space with air and several times and pump it out just to make sure that you've removed the whatever helium gas got into that space. Okay, so there's two sources of heat, conduction down like a solid wall and conduction by gas. The other thing that can happen is you've got a 77 Kelvin temperature region separated from a low temperature region at say 1 Kelvin or whatever, and so you're going to have some heat transferred by radiation. And so this would be radiation heat transfer. And so in this case, the heat load on your low temperature bath has three main sources: conduction by, or let's say conduction through some kind of solid structure, to conduction by a residual gas, and radiative heat transfer. And so we're going to look at all three of these probably in next week's lectures. And we're going to see how we can quantify those, and we'll come up with some strategies for mitigating these effects. So the total heat load is the sum from all of these contributions, and your base temperature is going to be set by when this sum of the net heat load is completely offset by the cooling power of your low temperature system. And although we've thought about this in terms of our pumped liquid helium bath, this is generally true for any system. However you're trying to get to low temperature, these are things that you'll always have to think about. Okay, good. So the next thing I want to do is, we've kind of alluded already to the fact that there's another isotope of helium, and so I want to see if we can come up with an experimental design for how you might get to low temperature using a pumped bath of liquid helium-3. But so the next topic is going to be experimental setup to reach. In this case, we'll get to maybe 300 millikelvin. So this is our first sub-Kelvin system. And the concept is the same. We're going to have a bath of liquid helium. This time it's the liquid helium-3, and we're going to use evaporative cooling. It's just that the helium-3 has a lower boiling temperature, and so we get to a lower final base temperature. Okay, first, let's just look at some of the interesting properties of helium-3. So the two isotopes are helium-3 and helium-4. So 3 means that the nucleus has 2 protons and 1 neutron. 4 means that the nucleus would have 2 protons and 2 neutrons. The natural abundance of helium-4 in naturally occurring helium gas is 99.999,863%. And so that means the helium-3 isotope is rare. So the ratio of the two is something like 7.3 times 10 to the 5 to 1. So it's about 1,000,000 to 1. Okay, the cost is 1 cubic centimeter of liquid helium-3 is about $150. It might be a little bit more than that now. So that means if you wanted a liter of liquid helium-3, 1 liter is 1,000 cubic centimeters, and so that's going to cost you $150,000 compared to 1 liter of liquid 4 helium, and that costs maybe around $13 these days. And so if you're going to go through the extra expense of getting liquid helium-3 so that you can go from a base temperature of 1 Kelvin to 300 millikelvin, you should have a very good reason for doing that, because it's going to be very expensive. Okay, usually the helium the helium-3 that's used in a low temperature experiment doesn't come from naturally occurring helium. It comes as a result of a byproduct in tritium production in nuclear reactors. And so the process is you take lithium and you have it interact with a neutron, and what occurs is a reaction where you get tritium and actually helium-4. And so this notation, let me remind you, the upper superscript on the left is the number of nucleons. And so for lithium, there's 6 protons and neutrons when you add them up. And the subscript on the left is the number of protons. So there's 3 protons in lithium. So that means the 6 tells us that there's 3 neutrons. The neutron, of course, has no protons and 1 neutron. Tritium has 3 nucleons. 2 of them are neutrons, 1 is a proton. And then helium has 4 nucleons, 2 protons and 2 neutrons. So anyways, there's no helium-3 in that reaction, but the tritium has a half-life of about 12 years, and it decays into a helium-3, so 2 protons and 1 neutron, plus an electron, and an antineutrino. Okay, and so what that meant is that if someone knew, for example, what a country's reserve of helium-3 was, then they would have a pretty good idea of what the activity of their nuclear reactors was. And so at one point, the amount of helium-3 possessed by the US government was classified information. Because it revealed how active the nuclear reactors were. One more bit of interesting information is that on the moon, they have these crater seas, and these craters are known to be a repository of high concentrations of helium-3. And so for many years now, there's been a sort of space race to see who will go to the moon first to retrieve helium-3 from the moon. In other words, people think that it might be economically viable to fly to the moon, capture a bunch of helium-3, and bring it back to Earth. Now, they're not going to bring it back to Earth so that physicists can do low-temperature experiments. What they're interested in is using helium-3 as an energy source. Energy source in fusion. So deuterium is a heavy hydrogen. So hydrogen is, its nucleus is just a proton. Deuterium has a proton and a neutron. And if you collide that with helium-3, a reaction occurs in which you can get helium-4 plus a proton plus some energy. And so what they want is that energy. Another possible reaction is helium-3 plus helium-3 goes to a helium-4 plus 2 protons, and again, plus some energy. The advantages of this process is that there's no radioactive products. you just get helium-4, which is not dangerous, and then you get some high energy protons, but you can control the high energy protons with electromagnetic fields. It's a charged particle, obviously, and so you can steer it and control it just with electric and magnetic fields. And then so you want to try to harvest that energy. Okay, so next here then is our apparatus for reaching 300 millikelvin. Okay, so let's see if I can draw this nicely. So we're going to have an outer dewar, and this outer dewar is going to be filled with pumped liquid for helium. And so this is at 1.2 Kelvin. So I've omitted the parts like you might have like another outer dewar that is at 77 Kelvin. And then of course the top of this dewar needs to be sealed because you're going to evacuate you're going to use a pump to reduce the vapor pressure. So I'm omitting that part of the drawing, okay? But what we drew at the beginning would be used to first get to 1.2 Kelvin. Okay, and then we're going to have an apparatus that's going to be like this little closed container that I'll try to draw. And then we're going to allow some pipes to feed through this container. Let me fix this up a little bit. Okay, so okay, good. And so, and then in here, I'm going to draw another little container. I'm going to change the color. Okay, so this is a little pot. It's copper or something like that. Okay, and then what we've got is a tube that connects like so. And then we've got a tube that connects over here. And actually, let me label a couple of things. I'm going to put a valve here. I'm going to call this valve 1, and then I'm going to put a pump over here, and I'm going to call this pump 1. Okay, and then over here, I've got another valve. And then this goes to another pump, pump 2, and this is actually going to be valve 3, and I'm going to have to remove this. I need a little more space. Because we've got valve 2 over here. And then we have a big tank that contains our helium-3 gas supply. So this is helium-3 gas at 300 Kelvin. Okay, this little copper pot here is maybe attached to the other enclosure with some thin stainless steel supports or something like that. Okay, so let's label some of this stuff. In here we have vacuum. These are stainless steel pipes. They're thin. They're made thin so that there's not a lot of material to conduct heat from the room temperature down into the low temperature apparatus. Over here this is all the liquid helium-4 at 1.2 Kelvin. This is maybe a copper chamber. This is stainless steel supports. And this is going to be what might be called a helium-3 pot. So that's where we're going to fill our liquid helium-3. Okay, this is a dewar. Okay, so what would be the steps used to get to low temperature, to get to sub-Kelvin temperatures? So this is reaching 300 millikelvin. So step 1 is the following. So with valve 1 open. So that means we're going to open the valve over here, and we're just going to evacuate the space that is between the liquid 4 helium bath at 1.2 Kelvin and where our eventual liquid helium-3 will be contained in our red helium-3 pot. And so we're going to use pump 1 to evacuate space between what will be our helium-3 pot and what we've called the copper chamber that's in contact with the 1.2 Kelvin bath. Okay, so we've evacuated that space, and in step 2, we're going to cool the copper chamber to 1.2 Kelvin using a pumped liquid 4 helium bath. Okay, so that means we've filled our dewar with the liquid helium-4, and we've pumped down the vapor pressure so that it gets to 1.2 Kelvin. Then what we're going to do is we're going to wait. We're going to wait for this red helium-3 pot to cool down to 1.2 Kelvin. And it will take a long time because it's connected to the copper chamber only through these thin stainless steel supports. And so those thin stainless steel supports aren't going to conduct heat very well. And so it's going to take a long time for the heat from the helium-3 pot to be removed by the pumped liquid helium-4 bath via the stainless steel supports. Okay, so we wait for the helium-3 pot to cool to 1.2 Kelvin via conduction through the stainless steel support. Okay, the time that it takes to cool can be. And what it's going to depend on are the heat capacity, heat capacity of the helium-3 pot, and the thermal resistance of the stainless steel support. Okay, so once we've weighed it, what we can do is we can open up valve 2 and we'll let the helium-3 gas enter into the helium-3 pot via the stainless steel tube. So helium-3 gas is going to flow down this tube and enter the pot. Because the pot is cold and helium-3 at 1 atmosphere of pressure will liquefy at around 3 Kelvin, it will liquefy and make a little pool of liquid helium-3. Okay, so we open valve 2 to let the helium-3 gas into the pot. That gas will cool to 1.2 Kelvin and liquefy. Okay, so now what we've got is our helium-3 inside here. And so this is our 3 helium bath. And now we're going to close off valve 2 and open valve 3 to the second pump, and we'll start reducing the vapor pressure above the liquid helium bath. So there's vapor above here, and we'll start using pump number 2 to reduce that vapor pressure. And as we reduce that vapor pressure, the boiling temperature of the liquid helium-3 will go down. So close valve 2 and open valve 3 to pump on the vapor pressure above the liquid helium-3. We can reach, using this method, typically around 300 millikelvin. Again, that base temperature will depend on the heat load on the liquid helium-3 bath, and so this heat load on the 3 helium pot are the same sorts of things that we already talked about. One is there's going to be radiation from the surrounding copper chamber. As we'll see later, because that copper chamber is quite cold, this radiation heat load is probably pretty low, but there could also be conduction by the residual gas inside the copper chamber. And so let's label these things Q dot radiation, Q dot gas, and 3, there can be conduction along the stainless steel support and pipe. So let's say Q dot conduction. And so if we label some of these things, let's say we have here, these are all Q dot conduction, Q dot conduction. If there's, well, okay, let's do the radiation one. So here's 1.2 Kelvin, and there's Q dot radiation. And if there's some gas in here, let's put some residual gas particles, then what we could have is Q dot from the gas. And so we would take that total heat load on our helium-3, pumped helium-3 bath, and the base temperature is going to be determined by that heat load balanced against the cooling power of the bath determined by the evaporation rate. Just before I stop, let me just point out that in step 5, it says that we're going to open valve 3 and pump on the liquid helium-3 vapor, and that's true, but we're not going to let the helium-3 just be pumped out into the room. Because the helium-3 gas is so expensive, you're going to have some kind of recovery system that is going to deposit the pumped helium-3 back into your original supply. So there'd be some kind of closed system where you're never going to lose any of that helium-3 gas. Okay, good. Thank you very much.